Module 3 is all about scientific method. The scientific method has some generic steps. Number 1, observe and question. Number 2, form a testable hypothesis. Number 3, collect data or conduct experiment to test the prediction. Number 4, interpret results. Number 5, to disseminate findings. So the first step is the observation and questioning. In observations, we never draw inferences. And inferences means just conclusions or extrapolation based on that observation. So let's go through some examples of these observations versus extrapolation. There was an axe next to the dead body. So this is just an objective observation. The axe was the murder weapon. So based off of the axe next to the bloody dead body, we can draw a conclusion or extrapolate that the axe potentially could be the murder weapon. So that is an inference. The axe at the crime scene was found 10 meters to the left of the body. So this is a description. The killer was left-handed and threw the axe to the left. So again, based off of that fact that we saw in the previous statement, the killer was left-handed is an inference. So that's not an observation. To create a good scientific question, you have to ask yourself, can that question have an answer and be tested? Can it be tested by some experiment or measurement that you can do? And does it build on what you already know? Okay, so for example, why is that a star? Is not as good as what are stars made of? Where does the sun come from is not as good as how will human skin react to solar radiation, where one participant is covered in SPF 30 sunscreen lotion and other participant is not covered in sunscreen lotion. And number 3, builds on what you already know, right? So will fertilizer make grass grow greener? It's not as good as what types of fertilizer will make grass grow greener. So the questions generated ask what and how in a way that focuses in on the specific problem to be studied. So it has to be framed in a way that that question can be tested. Okay, in the discussion board, hit reply and answer the following question. Which question in the question pairs is the better testable scientific question? For question number 3, determine whether it is a good question. And if it isn't, how do we make it better? I'll give y'all a minute and 30 seconds. So question 1A, what are the different things that make up air versus what is air? Number 2, why is the sun out today versus what atomic elements make up stars? And finally, question number 3, is more fertilizer better for plants? So match the term to the appropriate definition. Again, I want y'all to take time later on to match the terms. The answer is on the next slide. Whoa, spoiler alert, answers are here. Forming a hypothesis. A hypothesis is a testable statement. I like to call it the yes or no statement. Yes, it can happen, or no, it cannot happen. It often contains a prediction. Chocolate may or may not cause pimples. So this hypothesis is considered to be wishy-washy. It doesn't have a yes or no statement. The next one, I think salt in soil causes plants to grow slowly. So you have to remove yourself from the hypothesis. In other words, no, I think. There are ghosts affected by color of the light. So this is wrong because it is a question. So hypothesis should not be a question, it should be a statement. And a testable statement at that. Bacterial growth might be affected by temperature. Again, that word might. We don't want to be wishy-washy. Last but not least, sparrows are happier birds than eagles. So this one cannot be tested. How can we measure happiness in birds? So here's a summary of what we went over on the previous slide. If you haven't written it down in the independent note-taking process yesterday, please be sure to write it down later on. So a hypothesis is a written statement, not a question. Do not have I think, I predict. A hypothesis, it has to be testable, and it cannot be wishy-washy. If writing a hypothesis is tough for you, I have a formulaic way to write a hypothesis so you can always get it right on the AP exam. Write it as a if-then statement. If statement about the independent variable, then statement about the dependent variable. The second one is my favorite way to write a hypothesis, and that is to directly state the predicted relationship between two variables. And finally, state the difference you expect to find between the two groups. Let's go through some examples. The first one is the if-then statement. If a first-year student starts attending more lectures, then their exam scores will improve. Number two, the number of lectures attended by first-year students has a positive effect on their exam scores. So that's the predicted relationship. And number three, first-year students who attended most lectures will have better exam scores than those who attended fewer lectures. So that's comparing two groups. The null hypothesis predicts no relationship between two factors. In science, we want to determine if there is any correlation between the independent and dependent variable. So to state that there is no relationship and then using statistical analysis to determine if there is any correlation is a good way to conduct a scientific experiment. In the discussion board, type out a good hypothesis for your revised question. I'm giving y'all a minute or so to do so. Designing an experiment is crucial. It allows scientists to collect data. It is a process that is reproducible by which an idea is tested. All experiments need a control group and an experimental group. Okay, so the control group is used for comparison to the other group. The experimental group is defined as changing one variable in that group to see if there are any effects. It must have at least 3 replicates per group. There are variables as well in an experiment. The independent variable is the variable that we manipulate or change. I repeat, the independent variable is the variable or factor we manipulate or change. The dependent variable is the variable or factor we measure. And the controlled variable are all factors that are kept constant so that they don't affect the results. So a good design requires random assignment to groups, control of extraneous variables, manipulation of the independent variable, quantitative measurement of outcomes, and the comparison of participant groups. So these are key for designing a good scientific experiment. As you can see from our good example, we have a control group that has no fertilizer. So that's the baseline comparison. And then we have experimental groups that varies in the levels of fertilizers that's used. So these are common issues with experimental design. And when you're trying to come up with a design for that question number 1 on the free response, please keep these things in mind. Number 1, if your sample size is too small, it is a bad experiment. Number 2, no repeated trials, it could be luck. Number 3, uncontrolled variables. So again, which variable do you conclude affected the variable you're studying? Number 4, no control group, so no comparison. Number 5, more than one independent variable, so you're changing more than one thing. There are 2 types of data, y'all. Quantitative data, which are numbers, and qualitative data, which are non-numerical descriptions. So good practices in collecting data. Replication is the thing. It is the repeated measurements, okay? Sample size is the number of times a measurement is replicated. Accuracy is the true value. Precision is how close a series of values are to one another. And uncertainty is an estimate of how much a measured or calculated value differs from a true value. When interpreting results, a hypothesis is either accepted or rejected using two types of reasoning, inductive versus deductive. Let's use the example on the next slide to help us with the definition. Inductive reasoning. Here we see the intrepid detective walking into the scene with a blank slate. He has no presupposed ideas about what might have taken place. So he looks. There's the ash from her cigarette, so she couldn't have fallen from a great height. There's the glass from a broken window, but this might have already been broken when she arrived, or it may have been broken in a struggle. Does she have lacerations? Is her dress damp from the rain outside, or dry? And he goes on to gather information until he arrives at a conclusion. Deductive reasoning is Sherlock walks into a dank bedroom with the premise that there have been a rash of murders in this area, so the woman on the floor is likely another victim of that same predator, and that he gathers information from there. Blood, nicotine stains, ash in a corner, a fragment of glass, and narrows the scope of that available information until his premise is the only logical conclusion remaining. So to summarize, y'all, inductive is about looking at the facts first, then making a general statement or conclusion based on those facts. However, deductive reasoning is all about going into a situation or an experiment with some knowledge, using that knowledge to draw conclusion from the facts that are presented. What we've been describing so far is all about controlled experiments, or experiments done in the lab. Natural experiments are a natural event that acts as an experimental treatment in an ecosystem. These natural experiments often are observational studies that compare numbers. So, an example of this would be the effects on the weight of babies born in 4 districts in Beijing during the Olympics in 2008 versus the weight of babies born during the same period in 2007 and 2009. Babies were born heavier on average during 2008, therefore suggesting that air pollution does interfere with fetal development. So after the experiment, the results are analyzed and a conclusion is made. Things are never proved in science, y'all. Simply, we are waiting for technology to be created to continually test a concept in a new way. I don't want to hear this word, y'all, prove. Prove should never be in a science class or in science in general. We do not prove anything. We simply accept or reject a hypothesis over time developing a theory. So again, I don't want to hear that word prove. Environmental science presents unique challenges. There's no controlled planet with which we can compare Earth. So again, Earth is unique and we don't have other control groups to compare Earth to. It is difficult to determine what is better or worse for the environment because it takes time to understand those negative consequences and whether those negative consequences are linked to that specific situation. Environmental science has so many interacting parts. It is not easy to apply one system to another system. And finally, when people are unable to meet their basic needs, they are less likely to be interested in protecting the environment. That's it for today, y'all. Have a good one.